Hello and welcome to this week's joint astronomy colloquium from the Munich area here. So this is a first for us. We are very new to this, doing this colloquium under these special circumstances and doing it in an online way. We see that we have actually quite a lot of people ranging from Beijing all over the globe, even to the west coast in the US, where it must be very early. So welcome everybody. And so I think one thing technical which would be great for everyone is that if participants could switch off their own video stream, that saves bandwidth on our side and that gives better quality for everyone else to see. Also, if you want to communicate with us, we have muted you and you cannot unmute yourself. Please use the chat function so we monitor this during the talk. All over, we assume that we are dealing here with professionals, so we hope that we don't get much of Zoom bombing and stuff alike. So much for the technicalities. It's a pleasure for me to introduce Reinhard Genzel, our speaker today. Reinhard did his PhD in 1978 at the Max Planck Institute for Radio Astronomy in Bonn, went then as a postdoc to Harvard, and 2 years later as a Miller Fellow to the University of California, Berkeley, where he actually got a professorship in '81. And since 1986, he's back in Germany as a director of the Max Planck Institute for Extraterrestrial Physics, where he is leading a large group, which is devoting most of its time to instrument development and exploiting the novel facilities. And one of these facilities is the interferometer gravity, from which the very fascinating measurements of the galactic center are. And this is what Reinhard will talk about today. Reinhard, the stage is yours.
Yes, as experimentalists, one is proud to try new things, even if in difficult times, like we are now. And I'm very, very pleased to be here and speak to you on behalf of the Gravity Collaboration, coming from several European countries and the European Southern Observatory, and having developed over the last 15 years a novel instrument which has already been quite productive. And I will tell you today about some new work we've been doing, summarizing also the work we have been recently doing and how this fits into a worldwide effort of ever better understanding the black hole paradigm, testing it, and also in the same vein, of course, testing general relativity. Now, the particular occasion is that today in astronomy and astrophysics, we announced the detection of the Schwarzschild precession of one of the orbiting stars, which we've been tracking along with our colleagues in California for a long time. And as you will see, the detection of the Schwarzschild precession not only shows that Albert Einstein's theory has been verified once more in a slightly unusual situation, perhaps, but also gives us very important new information on the environment of the big black hole. Now, the field, as you well know, is one which has a long pedigree. It's 100 years since the work of Albert Einstein and Karl Schwarzschild, and I've summarized for you here some of the actors, both theoretical as well as observational, and I apologize if I couldn't fit many more faces on here, but it's absolutely a privilege to have been amongst all these giants and see whether general relativity is valid in a regime where it has not been tested. Now, as you well know, this all started after the theory itself got announced immediately with two experiments, the light bending, and then of course also the perihelion advance of Mercury, so the Schwarzschild precession of Mercury. Then in the 1950s, laboratory experiments started, followed by lots of work in the solar system, which explored the theory to ever higher degree and higher fiduciality. The pulsars have done enormous work in the field, testing to several of the post-Newtonian parameters. And then, of course, the gravitational waves coming with LIGO have been the ultimate highlight over the last few years, testing for the first time the theory in the regime just outside or in the regime of the event horizon, which is in this picture at the very top of the diagram. Now, this is at still relatively low mass. And if the theory might be wrong, it could be wrong if there's a mass dependence. So it's worthwhile and of interest to go ahead and test the theory also at high masses. So that started off with X-ray observations, also the discovery of a very broad relativistic X-ray line, which probably originates from accreting and orbiting gas, hot gas, in the immediate vicinity of the black hole. Last year saw the detection of the millimeter emission in a beautiful ring-like configuration around the very, very massive black hole M87. And so many people have been studying supermassive black holes, measured their masses with various techniques, and showed that they're very important in the history of galaxies and the centers of galaxies. Now, the Galactic Center has taken a special role in this, in that it is so close. And so we can train improving instrumentation onto this system and check out whether there might be a black hole there. That all got started in the 1970s by Charlie Towns, and then went on ever deeper and ever better. And what we are talking about today is just one such step on a long series of very successful observations, which have in many ways turned the Galactic Center into a wonderful laboratory, physics-like almost, to test the theory. So that has led us and our colleagues in California, Andrea Guess and others, to look at stars and their orbits in the immediate vicinity of the black hole and test the theory there. And the first set of results from both groups have come about, and I'll mention them a little later. And the next step is to go further in and make still more precise measurements of the theory. So that's the state of affairs. And let's start with the Galactic Center. And the first rather unusual situation, that whilst we thought that from theory that a big black hole should only be surrounded by stellar remnants, which are very long-lived, and or long-lived small stars, the reality is that we've seen many rather youngish objects whose origin actually at this point is still not fully clear, and theoretically was certainly not predicted. When that was discovered in the early 2000s, it became clear once the first orbits were measured by the two groups that a next series of measurements of higher precision, both in terms of the spectra of stars, but also in terms of the orbital parameters one could measure with big telescopes, could lead in the domain of testing the theory for the first time around a massive black hole directly. And indeed, around 2006, Tal Alexander and Shai Zucker wrote the first paper in a series of papers by a number of people who basically showed that it could be done if you would improve the instrumentation. Now, in particular, one star is important here, the star S2. It has a period, an orbital period of only 16 years. So actually, we've now seen it looking at this object for more than 2.5 decades, come around twice. We've seen two peri approaches. And after the first peri approach in 2002, we felt, well, what should we do? What can we do to measure post-Newtonian effects of gravity. One of the first effects you can think about is the gravitational redshift. Now, as you see here in the post-Newtonian expansion, that's an effect of the order of b beta squared, v over c squared. Now, the star S2 approaches on a highly elliptical orbit, the black hole, down to 17 light hours. That's about 3 times the orbital radius of Neptune. At that point, moves at about 7,600 kilometers per second, and the beta squared effects in the gravitational redshift, as you see, are just under 0.1%. So that's actually feasible, we felt. And our colleagues in California also felt that is feasible with spectroscopy, which already was available at that time, combined with adaptive optics on the big telescopes. So in the diagrams below, you can see the various effects as you go to more and more sophisticated exploration of the gravitational field. So the gravitational redshift compared to the Newtonian terms at Perry is about a 200 kilometer per second deviation, which modern spectrometers in principle can detect. The next term would be the spin term, the frame dragging to lens steering precession. Unfortunately, that's very small. As you see in this star, spectroscopically, that's about 1 kilometer per second. And then you can go to higher and higher orders. So clearly that's out of the picture for that star, but as you will see, maybe others can serve. So in 2005, we started building a new instrument in order to get into this regime here, to be able to test the theory at much higher level of degree. And for that, we used the combination of all the big ESO 8-meter telescopes. Now, let me say a few words then about interferometry. Interferometry, of course, is something that every radio astronomer knows is how you build big telescopes. Nobody would really, at this point, when wanting to have a higher resolution radio telescope, build a single dish radio telescope. You will build an array of telescopes with longer and longer baselines. Now, this array consists of individual 2 telescope interferometers, as you see in the top right there. When the wave of radio waves at wavelength lambda comes in, you have to correct for the geometrical path length difference. Then the interference of the 2 waves is dependent on the baseline, the orientation of the object, and the wavelength. So the larger the baseline in units of wavelengths, the better the resolution. So that's how you do high resolution work, and also astrometry at radio wavelength, culminating, of course, in the wonderful work with the Event Horizon Telescope, where you go to very short wavelength, 1 millimeter, and use the entire globe as a baseline, thereby going down to resolutions of about 30 micro-arc seconds, which was the basis of the wonderful result on M87 last year. Now, how about the optical? Well, in fact, interferometry was, a very important laboratory development in the late 19th century. And in fact, Michelson, the famous Michelson, built already in 1920 a device on top of the 120-inch Hooker telescope to basically use mirrors separated by different distances to then measure in interference the sizes of stars. So Michelson and Pease really started this in the 1920s, but that was already it, because very difficult work. Most everyone else felt it was too difficult and not worthwhile. And it took, a long time until the next attempt was made in the 1950s in Australia by Hanbury, Brown, and Twist. Now, they didn't use interference. They used the fact that when you look at a very bright star on the really gene side, there is a correlation, a quantum correlation, due to the bosonic state of photons, such that you get basically a correlation of the light from 2 telescopes, and you can measure the diameter of stars. That's difficult too, and actually not very sensitive. Charlie Towns, the Nobel laureate for the invention of the maser and the laser, was the next. He said, well, okay, the reason it's so difficult in the optical is because you're at short wavelengths, everything vibrates. So, you know, the fringes are very hard to track, as you will see in a second. Why not use the radio technique? The radio technique of basically moving a fairly narrow band down to a wavelength in the microwaves where you have amplifiers. So Towns built the first heterodyne interferometer detector for the 10 micron region, which was successfully used by him and his group until his death. So if you now compare the difficulty of doing infrared or optical interferometry relative to the radio, you account for several factors. The first one has to do with the control of the fringes, both in space, that's the spatial coherence, as well as in time, that's the temporal coherence. So as you see here, when you go to short wavelengths, typically your bandwidth increases, so your delta lambda increases. That makes the size of the fringe smaller, and therefore it makes it more difficult. So it's in the denominator. On the other hand, or the same way, because the size of the fringe is small, also the temporal coherence. So these first two factors are very much more beneficial for the radio than they are for the infrared. On the other hand, you go to shorter wavelengths, typically you go to hot sources and you basically walk up the Rayleigh-Jeans tail. So for high temperature, nu squared increases, and this is an advantage for the short wavelengths. And then finally, you must control the wavefront. If you want to do interference, you have to interfere flat wavefronts. Again, that's pretty easy in the radio, and it's very difficult in the infrared. So if you bring this all together, that's about a factor of 10 to the 5, roughly speaking. So that's why it took a long time for infrared and optical interferometry to come to the fore, and has not really been used for faint source interferometry. The next factor, which is not very advantageous for the infrared, is that for imaging interferometry, you would like, in the case of the very large array, combine many telescopes, not just two at a time, but many. And the radio can do this because you have very low noise, phase-sensitive amplifiers, so you can amplify the light before you split it, and then combine it without loss with many telescopes. That is not possible in the infrared and radio in optical because of so-called quantum noise. So when you split the light, you lose light. And so, in fact, the VLTI with 4 telescopes in many ways is sort of an optimum of doing faint source interferometry. It's big telescopes. They're very sensitive by themselves if you are able to align the waves, and you have wide bandwidth such that the coverage is also enhanced due to the different wavelengths. And finally, you really only have 6 baselines such that you don't lose too much light. Now, building such an instrument for the ESO VLTI was actually already on the minds of the fathers of the VLT. And I must say, their great foresight really made this all possible to bring us basically a system onto which we then could develop such a system. And this system we started under the leadership of Frank Eisenhower, as I said, around 2006, formed a collaboration with another Max Planck Institute, 2 French observatories, the Cologne University and the Porto University and ESO, and basically built this instrument we call gravity. And I want to show you how gravity works roughly. There are a number of key innovations in this system. One is due to the development at ESO Gerd Finger, we now have imaging detectors which we can read out at very fast rates during the coherence time of the atmosphere, 1 kilohertz, without really much noise. Next, we are basically putting all the beam combination into a door at low temperatures, so there's no thermal problems. We use monomode fibers to guide and also control the waves, integrated beam combination to make the beam combination very efficient. Very importantly, we use very much like radio work, phase referenced work, so that we can detect the fringes on a bright star and then integrate for a long period of time on a faint star and thereby improve the sensitivity, as you will see, by a factor of more than 1,000 compared to what has been possible before. Now, this has to be done with adaptive optics too, because the 8-meter telescopes, of course, by themselves are not coherent. You have to use adaptive optics. Now, it's clear everything here is on the nanometer scale, and so you have to have metrology with lasers going through the system, which basically give you exact knowledge of the path length differences. So now I want to show you this, and perhaps some of you have seen this wonderful movie we've made to demonstrate how complicated this instrument really is. And we've called this movie The Last Millisecond of a Tortured Photon. So basically here's the beam coming from the galactic center, hitting in the Atacama Desert, the primary, and then the secondary and the tertiary. So far, so good. Now, however, we have to go and bring the beam down into the basement of the Coude in order to allow the combination. And there's a lot of mirrors here, so that actually is not so good for the sensitivity. In the basement, we now actually analyze the wavefronts. This is for the adaptive optic systems on the telescope. This is done for each of the 4 telescopes. Then underneath this tunnel here has little carriages which removes the geometric path length difference to first order so that you're near the fringe, although not on it. Now the 4 beams from our 4 telescopes go into the cryogenic environment of our door. We need to manipulate them, we need to calibrate them, and then we have to pick out 2 positions on the sky which we would like to analyze. They have to be within about 2 arc seconds of each other in order to fit through the optics of the system. So you see this happens for all the 4 telescopes. Here is the analysis of the beams, K-mirrors, and so forth. I don't want to get into many of the details. So now you have for each telescope 2 beams, for the fringe tracking beam and the science beam, and those you then put into the fibers, these monomode fibers, which keeps the system compact and guide now the light. So let's go along the science beam. Now here we have to correct a little more for the delays because of vibrations in the system and the atmosphere. So these are differential delay lines we can pull and push. We can also manipulate the polarization of the beams before they come together. So here we now have our 4 beams. The same is happening for the fringe tracker, and go into the beam combiner where a special chip now makes all the combinations. The chip is about this half the size of your hand. There you see a picture. You come in with 4 beams and you make all the combinations. You also make phase shifts so that the outcoming light then can be directly analyzed once you've split the light in a spectrometer. So that's where we are, and that's where the photon, after all of that torture, ends up. Now, not many of the photons make it there because the efficiency actually is still challenged by the many mirrors, and so there are lots of more improvements we can think about. Now let's go to the galactic center. So I told you about the star S2, which we in the UCLA group have been looking at now for more than 2.5 decades. One gets older as one works on it, but it's getting more exciting. So we started off initially with a smaller telescope, the NTT, and that started in '92. Then at the first Peri near Sagittarius star, which is a cross down there, you see also red dots. I'll explain that in a second. That's where the star is only 17 light hours away from the black hole, and then goes back out. So that first Peri happened in 2002, which both groups caught, and then it went back out, and that's now done with adaptive optics on the 8-meter telescope with NACO in our case, and NERC2, the KEC adaptive optics system. And then in 2010, the star reached Apo out there, was very slow, relatively speaking, and then was starting to come in. In the meantime, we were working on gravity. So you see, one of the things we had, we were quite on time pressure here, because we knew the next Peri was going to be in 2018, so we had to be there. And Frank and his team did a marvelous job together with ESO to get that good going. And by late 16, we were on the telescope. There you see the first data point, perhaps on the right side is a little blue. That's the first data point we took. Then in 17, we were on. And then in 18, we were seeing the Peri, and now we're going back out. So with the VLT and the interferometry, a number of things have changed. When you look at an adaptive optics image on the left side there, S2 is one star amongst many. It's the brightest, but there are others. And in fact, at times when the stars are all moving there, they are, basically confusing each other in terms of overlapping light. And so at some of the epochs, in fact, you have to be cautious because you're not looking at one star, but you may be looking at two. So those data points you have to actually eliminate. With the interferometer, that's on the right side, that is totally different. First of all, you see only one star, S2, but you also see the black hole. Now we knew that the black hole was radiating from time to time. We call that flares, and I'll come back to that later. But we didn't know that basically the black hole is visible at all times. So that means that during the critical Peri period, it's possible with interferometry to make a very simple triangulation. You basically see a binary and you can measure very precisely. So in fact, during the key period around the Peri of the star in May 2018, when the star is, as I said, moving almost 8,000 kilometers per second, we could see the motion of the star, as you see here, the red dots, from day to day, not with adaptive optics from year to year or month to month, day to day by about 400 microarcsecond a day. And that's fairly easy with the interferometer. And you could immediately measure the precision, at high precision, the distance between Sagittarius A star and S2. So the accuracy of the astrometry is about 10 times or better at times than what we can achieve with adaptive optics. So that's a key thing. At the same time, I mentioned to you the capability of reference imaging. The reference star we are using here is 1 arcseconds away. It's this object up here called IRS-16 center. Maybe you can see it in the left image there. That's 10th magnitude and is bright enough to be detected with the interferometer in the coherence time. And so we use it to stabilize the fringes and then integrate on S2. And in the faintest, best images, we went as deep as K of 21, which is really a number to be proud of and gives us hope in the future to see perhaps even fainter objects than the ones. Then the spectroscopy we also do, in our case with Symphony, in the case of the KEC group with OSIRIS, and we are basically tracing here the radial velocity of these absorption lines due to bracket gamma and helium. So that's the data. So we have many, many epochs. The last data, of course, we could only get before the coronavirus stopped us this year, and I believe the Keck group as well. We are eager, of course, to go back to the telescope, but at least we have one measurement already this year, which is not on these data. So now let me discuss again the GR effects and the redshift, the gravitational redshift. So that's what was predicted. This 200 kilometer per second residual between a Newtonian orbit and the GR orbit. And I go straight into the result as they are of now. So here you see that's the result we've gotten in the meantime on S2, removing from the best fitting GR orbit the Kepler part, and then you can see the theoretical expectation for GR, which would be for this fudge factor of unity and the data. And there's a very, very good agreement. So we are now at a level of only about 2.5–3% of the effect. Likewise, our Keck colleagues also saw that effect. So that was the first thing we were able to show, that the gravitational redshift can be detected. Now, actually, the gravitational redshift has another aspect to it, and I'll come to that in a second. Let's talk about precision. Now, initially, you would think, well, okay, this effect is in wavelength, so why don't you only use spectroscopy? I mean, why do you need interferometry for this? Well, the answer is, in order to get these results, you have to fit for 14 parameters, and there are many degeneracies. So there is a possibility, if your astrometry is not good enough, that a Kepler orbit, not a GR orbit, in wavelength space looks pretty much the same as your GR orbit. So that makes the significance of your result not as large. So that's the purpose of the astrometry for this particular measurement, is to really nail down the astrometry and thereby sharpen the accuracy of the result. And you see, we can now determine, in fact, the mass of the black hole statistically to about 0.1%. But there are also systematic effects, probably 2.5 times, 3 times larger. We know the distance to the galactic center to 1.1%, and again, 5 times probably worse in systematics. So that is a very important number for much of the galactic community, and in fact, the Gaia community has been using this result fruitfully for their research already. Now, as I said, the gravitational redshift has a further meaning, and that's in the weak Einsteinian equivalence principle, or the local positional invariance, basically stating that if you're in free fall, then the physics shouldn't depend on what kind of a substance you are. So if you write the gravitational redshift delta nu over nu proportional to the differential in gravitational potential delta phi over c squared with a arbitrary deviation factor beta, 1 plus beta, then GR predicts that beta should be different, should be equal to 0 for all substances. Or if you measure it with different clocks, different substances, then you should see a delta beta which is vanishing. And indeed, we have 2 clocks. One is a hydrogen clock, and the other one is a helium clock. And we could establish here that the equivalence principle is correct also around a massive black hole to about 3% or 4%. So that's the results we had until recently. I come back to the immediate environment of the black hole at the end. Let's go next to the Schwarzschild precession. So the Schwarzschild precession also is an effect of beta squared, but now in space. It means that even if you have no perturbation, a motion of a single star around another object, a massive object, is not closed anymore like it is in Newtonian physics. And so this this precession in plane of the orbit was calculated by Albert Einstein. And in fact, what you see below is a photograph I made when I was visiting Jerusalem and the Einsteinian archives of his calculation. And as you may recall, that of course, that was one of the first results which was tested in GR, because the Mercury precession was known and there was a missing or not understood 48 arc seconds, which the Einstein's theory then showed. Now, in the case of S2, we immediately can predict what we should be seeing. So what you see here on the left and the right are the residuals in X, right ascension, and declination as a function of time relative to a non-GR orbit. So it's the residuals between a full GR orbit and a non-GR orbit. And then we null the phase of the orbit such that at APO of 2010.35, we call that 0. Then what the effect, the precession looks like in X and Y space is basically nothing for a long time until the star approaches the black hole for the next peri in 2018, and then a very rapid change, a kink in the direction of the orbit. So that's not like if you had a circular orbit. There the precession would be continuous with the same angular speed. This is not true for an elliptical orbit. For an elliptical orbit, it's basically nothing happens at APO, and then there's a very rapid change. And it's mostly in RA, as you see currently. Now you can take the RA and the deck information and turn this into an angle. And you do the same thing, then it's what's below. So you start off at 0 angle. Then there is basically a change when there's basically a very rapid change, which looks like a delta function when you're computing the residuals. And then you come out on the other side and nothing happens. And you end up at, in this case, 14 arc minutes. Now the true angle, I should say, is 11.9 arc minutes. But of course, the orbit is not in the plane of the sky. So you have to consider this in this case. But that's what we're after. We're looking at this kink in the motion. And so measuring right at peri is a very, very important thing. Now, in principle, actually, if you look at the number of 0.5, 0.6 milliarc seconds, that's something which we can, in principle, do with adaptive optics. So why have we and the Keck group not done that yet? Well, because you need to know where 0 is. You need to know where 0 in X, Y, and VZ is for the black hole. And it's this technical difficulty which has actually prevented us from getting a result. So the way we solve this with gravity and all the other measurements is as follows. When the star is not moving much at APO, we can average the motion over many epochs and get basically a 0. Then when it comes in, we then use the interferometry. We can precisely measure that kink. And we are helped actually in all of this with the fact that the flares, to our knowledge, basically come from Sagittarius A star itself. So whenever there's a flare on, we can calibrate the zeros for the adaptive optics measurements. So that's how this is done. And here's the result. So in the bottom, let's look at the bottom. Here again are the residuals in X and the residuals in Y. And you see these horizontal gray bars. Well, that's the average over the APO times over 10 years in the adaptive optics measurements and their uncertainties. So that's 0. And then you can see how in X in particular, around peri, which is that vertical line, the gravity measurements very nicely can see the kink. You can also plot this in terms of the angle on the sky, as I explained before, on the upper right. And there you see, you come in at angle 0 and you go out at angle around 10 arc minutes, which is what is predicted from the theory. You actually see the effect even in the velocity as a residual effect, but I don't want to go into that detail. So we have a detection. How good is the detection? Well, it's roughly 5 to 6 sigma at this point, independent of how you do it, whether you make a classical a posteriori fit or MCMC. The methodology really doesn't make any difference. The reason it's not infinitely good is, again, the degeneracy, despite the very precise way of measuring it. And the greatest culprit is this difficulty of knowing with the adaptive optics measurements where x where 0 is in x. So you can see here the MCMC covariance between RA of 0, 0 versus the Schwartz fudge parameter, which is 1 for the general relativity and 0 for Newtonian. So you can see you have to measure to much better than 1/10 of a milliarc second. And that is difficult with systematic effects, but it's possible, as you see from these measurements. Now I come back to the meaning of this in terms of astrophysics. It's certainly wonderful to confirm the theory with this famous effect called the Schwarzschild precession, but actually there's more to it, and I'll come back to this. But let me first go now further inwards, and let's look at Sagittarius star itself. It varies in its output continuously. From work of Gunther Witzel and others, and Dodds Eden, you see here basically a long time series of near-infrared measurements where you see that it goes up and down and up and down. What we're seeing here is synchrotron emission from very hot electrons. Most of the electrons in the innermost region around the black hole, around the event horizon, are virialized at a gamma of about 10. That's not enough to make synchrotron emission in the infrared. It's enough to make synchrotron emission in the radio, but not in the infrared, certainly not at X-rays. But if you accelerate the electrons for a little while, make them gamma of 1,000, then they radiate throughout the infrared. And if you accelerate them to 100,000 or 1,000,000, then they radiate in X-rays. So that's why we believe, due to interaction between magnetic fields, reconnection, etc., there's variable infrared and X-ray emission, which we can see in the infrared at least most of the time, in X-rays only sporadically. And it's this which we have also looked at with the interferometer. And in fact, our first paper came out in 2018, and we are working on still more data. Now, the emission from Sagittarius A star, we have now studied with gravity in some detail. And we can actually, because we pinpoint it so very clearly and there's no confusion, can definitely say that the emission in flux is not just a log normal distribution, but then has some excess at high fluxes, which we would call the flares. So something physically is happening there, which may be, maybe thunderstorms and these hotspots generated by reconnection. That's at least a valid hypothesis. And in 2018, we were able to see 3 such events, in July 2 and in May 1. And we actually were able to see that there is a motion. Now, what you see here is basically 0, 0, 0 is as best as we can make it out to about 30 microarc seconds, the position of the black hole, the position of the mass. And then always the dark colors are the early time measurements. And then on a scale which you see on the right, you see a motion, a clockwise motion with an amplitude of about 50 to 100 microarc seconds. Now, not all the measurements are very good. There's some jagged lines. So, we still need to do better on this, but clearly we see motion on the scale of a few times the event horizon. Now, theoretically, what you might actually be seeing is this. It's a combination of a motion of a bright spot, lensing multiple imagery, etc., etc. It depends very much on the orientation and the spin parameter, etc. A recent paper from the gravity collaboration has looked at that in some detail and has been published recently. And so what we are doing with gravity is measuring the centroid of this. So sometimes you may be seeing what looks like a good motion. Sometimes you may be seeing a combination of motion and lensing. Another thing we can observe is the polarization. And when we did that, sure enough, the polarization was also changing, right, in a continuous way. Let's just look at the bottom where you can see the orientation in the Q and U Stokes parameters of that flare, and you can see it's a loop. In fact, a loop which has the same orbital period as the orbital period of the apparent clockwise motion on the sky. Now that's actually surprising. If you think of the black hole at the center here, where you cut here in a way that the accretion disk is into the plane of the paper here, then you have a magnetic field which can be polar near the black hole, and then basically bends into the accretion disk, threaded into the accretion disk. And if the gas density is high, then everyone would assume that the magnetic fields get frozen into the accretion disk and dragged around by the motion of the gas into a toroidal configuration. But if you compute then the polarization patterns of such a motion, you get east and west occurring twice during your orbit, not once, twice. If you only have a poloidal field which goes straight up, and you look at that from above, then you see no motion. So the fact that we see one loop is probably a combination of a very strong poloidal field with a combination of a radial field. Another paper in preparation has been looking at that in some detail, and there you see some of the results of that. Now, of course, that's very, very exciting because understanding innermost accretion zone around such a black hole is of utmost astrophysical interest to see the jet production zone, etc., etc. Let's just look at the motion, though. So we have a period, approximately, of 45 plus minus 15 minutes, and we have an approximate radius after correction for the broadening due to the measurements. And so what you see here are these three flares in black, in magenta, and then in blue in the arrow bars. And then you also see a red dot. That's the innermost stable orbit for a Schwarzschild hole of 4 million solar masses. A green dot, that's the innermost stable orbit of an extreme Kerr hole in a prograde motion, and a black dot, which is the ISCO for a retrograde orbit. And you see the measurements, broadly speaking, are consistent with motion just outside of a near Schwarzschild hole. Importantly, they also agree to within the uncertainties with the mass. So here we have, for the first time, a plausible measurement of a mass right outside of the event horizon. That's extremely exciting, but we need to go on. Obviously, we wouldn't want to do this. We have more flares. We're analyzing them here. I should say another part of the story here is we can say something about a geometry, and we learn something about what are the angles of the accretion zone. And we are learning that the accretion zone probably is strongly influenced by the angular momentum of the gas coming from stars just outside of the event horizon region. So now let me summarize. 35 years ago, when I got into this, Charlie Towns was already fairly convinced that there would be a black hole. Few others were. At that time, there were measurements of stars at tens of parsecs and a bit of motion of gas around 1 parsec. And this is what you see here, the enclosed mass as a function of galactocentric radius. And you see there's a sort of an increase, that's the extended stellar nucleus, but then there's sort of a flattening. That's the evidence we had at the time. Now, if you compare this to what we now know, we've gone inwards by a factor of 1,000,000, all the way up to the event horizon size. It's always about the same mass. So that's extremely encouraging that we really are looking at a black hole. Now, of course, we would like to measure its spin. We would like to still go further, but it's exciting to see how well we can really make a case for a massive black hole. Now, not only the black hole itself is interesting, but also its environment. The fact that the Schwarzschild precession is so close to what GR tells us immediately tells us there cannot be much extended mass around the black hole. And in fact, the limit we now have is given by this upper arrow in blue, about 0.1% of the mass of the black hole. Now, there ought to be something. And the question is, what could there be? Well, there could be stellar black holes, which have migrated inwards. There could be other stars which we haven't seen, and we are hunting them down. And there could be intermediate mass black holes. But here again, the fact that the Schwarzschild precession is so close is an extremely good tool to investigate what we can say about a black hole, another black hole in the innermost region. So here's a simulation from two of our postdocs of an intermediate mass black hole of about 3,000 solar masses in an orbit just inside of the S2 orbit. If the orbits cross, then this system is not stable. So that's for sure. The stability of the S2 system by itself already tells us there cannot be things in too large numbers. But if there is a massive black hole inside, it really massively changes the orbit in X and Y and also in velocity, as you see on the right. So we've used that information to constrain how much mass and at what distance from the black hole could be present. And you see in this diagram, there's hardly anything left. There are two little holes just inside and just outside of the S2 orbit, where maybe an intermediate mass black hole of 100 solar mass object could fit. Everything else is excluded. Certainly the object cannot be binary and have any massive objects nearby. Of course, this can also be done better in the future with other stars, perhaps, etc. So let's, in the end, think about the future. Are we done? Have we proven that there are massive black holes? Or can we exclude other theories of gravity? Well, actually, what everyone wants to do, us as well as the event horizon community, as well as the gravitational wave community, is to basically make a test that the curve metric really is true on the scale of the event horizon. So in the words of No Hair, you want to show that the quadrupole moment of the black hole is totally determined by the mass and the spin, and that there is no other parameter, epsilon, which would have to be included and is included in some of the theories. Where do we stand on epsilon as a unitless number? Well, the AGNs, the reverberation of the K alpha line has probably already excluded epsilon of a few. The first in-spiral 30 solar mass LIGO system has settled that to 0.4, 0.5. So that's already fairly significant. The hotspots we see near ISCO is probably a little worse, but comparable. But then let's look what's coming. If the Event Horizon Telescope can actually measure the photon ring and compare this to our 0.1% mass estimate, we can go down to 0.5 if indeed it is like that. If gravity sees faint stars and can measure the spin, we can still go further down. If you can combine gravity and precision measurements of the photon orbit, we are down at a 0.1. If there is a pulsar, which the radio astronomers are looking very hard, that could be equally useful. With the ELT, in a few years' time, we might be able to make a few tens of meters to 100 meter per second spectroscopy of faint stars, pushing this still further. And then 20 years from now, the champion of us all is a LISA extreme mass ratio in spiral, which should settle the problem for all. Now, it's taken 100 years to get here, but it's been an exciting period, and I hope it will continue. Thank you for joining.
Yeah, thanks a lot, Reinhard. So you see we have a small audience here, of course, following the distance rules. We would like now to try a question and answer session. The way it can work is via the chat function, because we have over 300 participants on Zoom and we have around 250 on YouTube. So please to write your questions into the respective chat functions, and we try them to read those questions and Reinhard can answer them. So please go ahead. So there's a question from Shai Zucker. Do you think adding data pertaining to other stars can improve the detection and maybe help to detect other post-Newtonian effects?
Yes, we have looked at that, Shai, already. And in particular with reference to the X0, Y0 problem, which I mentioned. And the answer is that the data with gravity and S2 are so spectacular that the help from the other stars is modest. They're helping some, but I think we should look at that more in the future.
Okay, there's a Shai says thanks. There's another question coming from, I hope I pronounce it correctly, Mordecai McLeod, asking whether has an all data analysis combining the Munich and LA data sets yet been done for the Parry precision?
The answer is no. Now, in principle, it can be done to some extent from the published work. In Tuando's paper, measurements have been published, which we can use and we have actually used, but there's some additional information again on the reference frame, which makes it a little hard to do this. I personally feel it's the right time now for the two groups come together and do it together. Andrea has in the past felt that it's more honest if the groups basically act independently. Then it's easier for you, the audience, to judge what's right and what's wrong. I would say I'm happy to at this point do that and see whether we can understand all the details.
Okay, thank you. Also here, Fabian Schmidt is asking. I remember from my undergraduate days, which for him are 14 years ago, that the supermassive black hole mass was 3 × 10⁶. When and why did it increase by 30%?
Yeah, Fabian, the answer is very simple. At that time, we did not have orbits, okay? So what we had to do is statistical estimates. So basically we used mass estimators based on a number of stars and using their velocity dispersion. And that, in fact, you make a number of assumptions in there about the eccentricities and so forth, which was at the origin of the lower mass. As soon as we had the first orbits, the mass immediately became as large as it is. Now, of course, in more detail, then it does depend on the distance. And indeed, there are still some items where we need to understand slight differences between the two groups.
Okay, thank you. Andrea Gies is asking, First, it's a compliment. It's great to see all the interferometric measurements. And she's then asking, I'm curious about the systematic uncertainties as precession is highly determined with the reference frame. It looks like the systematic uncertainties are about a factor of 5 larger than the statistical uncertainties for R0 and E between your redshift paper and this one. What is the systematic in precession?
Yeah, Andrea, you're in principle fully right. Now, the reason for the rather large change in distance between the July 2018 paper and now, which is disturbing, is explained in this paper in the first part of the appendix. At that time, we were surprised, positively surprised, that we could use a single placing of the fiber where we had the star and Sagittarius star at the same time and basically use the binary fitting technique. We didn't think that would be the case because we didn't know that the black hole would be on all the time. Now, this was early times in making these measurements. And so moving from S2 to Sagittarius A star and back, you lose time. So we immediately jumped into this binary single beam technique, not knowing that there were aberrations as a function of distance from the center of the fiber. And so it turns out we had to learn these now, and that's described in the paper. Once you put these corrections in, the distance always has been 8250. So the change from 8150 or 60 to 8250 is an instrumental effect which we were not aware of. But it does not change, by the way, the significance of the significance of the 2018 gravitational redshift.
Okay, thanks. The next question from Rustan Gainutinov. Is the pericenter shift of some other S-stars, for example S14, also detectable?
Yeah. Now, with the interferometric technique, you have to be aware this is very costly. A good measurement with S2, you have to invest certainly 5-6 epochs per year, and then each epoch, at least 1 or 2 days. There's calibration measurements, etc., etc. We are using 4 telescopes per night, so we cannot, and up to this point, we had to concentrate on one problem, which was the S2 problem. Obviously now we can begin to look into other stars, etc., etc. Now S14, I forget, when is it coming back? In 10 years or something like this? I'll be dead by that time, but the young ones, can have a good fun with that.
Okay, we actually have also a question from the other channel here. Georgios Papasel might have missed it, but he is asking whether there was a constraint on the spin of the black hole from the innermost stable circular orbit results.
Yeah, well, not yet, I would say, not yet. I mean, certainly it's not an extreme curve. That doesn't look like that, right? So I would think it's more likely to be low angular momentum. But I think we need to go the next step on that, which is the work for this year, to analyze other flares, and then by averaging flares, get to a more significant measurement of the inclination parameters, etc., of the innermost region.
Okay, thank you. Li Jiangshao is asking, what is the estimated timescale to achieve 1% tests of the no-hair theorem?
Well, I try to give you my view, which is hopefully not too optimistic. Again, I'm betting, of course, in the end on LISA, I have to say, because it is the ultimate experiment, but that's still a long time. So if you insist to do this on the ground, I'm a little suspicious that LIGO will not be good enough, basically because with a stellar black hole, or in spiral of a stellar black hole, you don't have enough measurement time to measure the ring down accurately enough. I mean, you get it at some level, but not accurately enough. But others should comment on this. Maybe Alessandra, if she's on, could comment on this. So I would say, I personally very much look forward and hope that the Event Horizon Telescope and gravity together can make a joint step forward. Whether that is 1% test of the no-hair theorem, I would say that's a little presumptuous, I would say, at this point.
There's a follow-up question from Georgios Papas. Are there any constraints on the spin?
Are there any constraints on the spin? Well, okay. I mean, it depends on your preconceived notions, right? I mean, if you think we should be seeing these motions just outside of ISCO, then this does not look like an extreme curve. It could be retrograde. Also, please keep in mind that the expectation theoretically here for a black hole in the galactic center is not that the Bardeen-Peterson effect would align the accretion disk with the central spin direction. So you may get because of the low accretion rates, the high temperature, the low density of the plasma. This has all been done lately by Sean Ressler and others from simulations. You would expect the accretion to be much more irregular.
Okay, thank you. There's one last question so far from Prasenjit Zaha. Congratulations on these beautiful results. Pardon my asking about a small detail. For the equivalence principle argument, the hydrogen and helium clocks are part of the same star. Are we then justified in considering them as independent?
The referee thought yes. What do you think? He says he will think some more. We'll be gladly taking your inputs into account, Prasenjit.
Okay, it seems we have reached a natural end of the question session. So thanks everyone for joining us. It was a new, but I think also a very great experience here. We hope you have enjoyed, you've learned something. And thanks again. Have a good day. Stay safe. Stay healthy.
Thank you very much for coming.